Hey everyone, the art of recursion is what we are diving into today. Let's jump right in. Recursion is a technique where large problems are solved by reducing them into small problems of the same form. Now, in code, that usually means writing a function that calls itself each time with a slightly simpler input until it reaches a base case. The key is to spot a pattern where we can break down a big complex problem down into smaller versions of the same problem. So that's easier said than done, right? Because recursion isn't something that we come across in our everyday life, unlike loops or conditional constructs. But hopefully, by the end of this video, you can learn how to develop the intuition that is necessary to make recursion seem as natural as some of the other control structures. So, with that, let's go over what we will cover in this video. We will step through a challenge involving a binary tree and trace the recursive process. Most introductory videos will either talk about Fibonacci or factorial, but I thought of using binary tree because recursion is widely used to solve real-world problems that involve trees. We will also understand by what it means to take the recursive leap of faith. It is mind boggling how many algorithms and Leetcode style questions require recursion. So, like graph and tree traversals, divide and conquer algorithms, dynamic programming, and backtracking techniques. I have only listed a few of them here. We will be reviewing Leetcode question 104, which says given the root of a binary tree, return its maximum depth. So, what exactly is the maximum depth of a binary tree? A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. Let's visualize what that looks like. So, in this binary tree, node D is the furthest away from the root node A. So, the maximum depth of this tree is 3. Let me go ahead and add a subtree to node C. So now the maximum depth of this binary tree is 4. All right, so let's think about how we can solve this. Well, one way is to do a depth first search, which is to go all the way down each path and keep track of the maximum depth using some sort of a global variable. Or we could do a breadth first search and count levels. But there is a really clean recursive way of doing it, so let's break that down. We are given a root node and we are asked what's the longest path from this node to a leaf. The root node is A and it has two children B and C. Let's just slide those to the side for now and zoom in on what's happening. Now, if you observe the left and the right subtrees on their own, it's basically the same problem again, just on a smaller scale. You are still being asked to find the maximum depth from a node. And if you break the tree down like the way I just did, each part turns into its own little version of the original problem. And here is the cool part. If the left and the right subtrees for a given node can tell me their maximum depths, I just need to take the maximum of the two and add one for myself. So that's it. Each node just needs to delegate the work to its children, ask them for their max depths. Then take the larger of the two and add one to calculate the result. It sends the result back to the parent, and this process continues all the way up. So by the time we reach the root, we have the final cumulative result ready. Now, this will all make more sense as we walk through the call stack step by step later in the video, so do stick around for that. Now, what happens when we reach a leaf node or we reach a node where its child is none? If we don't handle that, we will end up with an error. So that becomes our base case where we simply say, if the node is none, return 0. So it should be pretty straightforward to convert this recursive formula into code, and we will review that next. But before we do that, if you are enjoying the content of this video, please do not forget to like and subscribe to my channel. If you have any feedback, I will really appreciate that. And you can leave that in the comment section below. Thank you. Let's now review the code. The function maxDepth takes a node as a parameter. The first thing we'll do is add the base case or the stop condition, which is if node is none, return 0. Next, we will recursively run the maxDepth function on the left and the right child nodes. Take the maximum of the two and add 1 to it and return the maximum depth. The time and space complexity of this solution is O of n, where n is the total number of nodes in a binary tree. And that is because we visit each node exactly once. To sum it up, here's what an anatomy or a typical recursive function looks like. It will always have a base case which is meant to stop the recursion. It will have a recursive step where the function calls itself but with a smaller input. So next we will walk through the function call stack of maximum depth and see out how it unfolds. Here is our binary tree, and this is the function call for the root node, which is A. It is recursively calling the maxDepth function for the left node B and the right node C. So let's process this function for the left node first, which is B. Now, a new instance of the maxDepth function is created in memory, but this time with node B as the parameter. The function call for node A stays in memory until the call for node B returns its result. Each recursive call has its own space in memory, so this instance runs independently to calculate the depth starting from node B. So that's how the recursion call stack is formed. And from here, we move left again to node D. It's the same thing here. Node B's function call sticks around in memory until node D is done and sends back its result. So from node D, we move left again to none. When we execute the maxDepth function for none, we hit the base case and this function call returns 0. Once 0 is returned, the function call to none is removed from the memory. Now our call stack starts to unwind. At node D, another function call is made for its right child, which is none. I'm skipping the visual for this, but it's the same kind of call we just saw, and it also returns 0. With both left and right child nodes complete, this call now returns 1 to its caller. Here also, another maxDepth function call is made for the right child of node B, and that points to none. So this also returns 0. The maximum depth at node B is computed as 2 and is returned to the previous function call. We are back at node A, and from here, a new maxDepth function call is made for node C. Since both of node C's children are none, the recursive calls for them return 0. That means the maxDepth at node C is 1, and this value is returned back to the calling function. The maxDepth at node A is calculated as 3, which is also the final answer. The whole point of doing this walkthrough was to show you how the computer handles recursive functions just like any other function, and to help you see how the call stack builds and then unwinds step by step. When you're trying to understand a recursive program, don't worry about all the layers at once. Just focus on one level. At that level, you can assume that the recursive calls will give you the correct answer as long as they are working on or with a smaller input. This mindset is called the recursive leap of faith. It means trusting that recursion works on smaller problems so you can focus on solving your part of the puzzle. It's the key idea when working with recursion. The more problems you practice with recursion, the clearer this concept will become. Like everything else in life, experience will make it easier. Thank you so much for taking the time to watch this video. I will see you in my next one. Goodbye.